Good afternoon, everyone. Welcome to the first Talk Colloquium of the year. Happy that everyone came today. I'm very happy to introduce Felipe Fidalgo, who is visiting us from the Federal University of Santa Catarina in Brazil. And he's actually visiting for a while, so he'll be here until August. So if you see this talk and you say, hey, this is great research, I'd love to work with Felipe, he'll be around and I'm sure he'd love to talk to you. So his research experience is on distance geometry, geometric algebra, and applications. So he's visiting Henry Volkovitz. And please take it away.
Thank you, Sam. First of all, I'd like to thank to the department, CNO, to have the opportunity to be here. And Henry could not be here today, but I want to address to him like in the video to say thank you for everything. This is not about what we've been researching here, but I tried to get a theme that could be that could access most of discrete math, combinatorics, a little bit of optimization, and what I've been doing in my in the beginning. This was from the beginning of my career as a researcher after my PhD, and I decided to talk about this when I saw Leo's presentation in the PhD proposal, because I saw lots of submatrices like touching each other, and I said, wow, it seems to be like it can be close. And I told Leo, I will talk about this. I don't know if it's the same thing or if we can work together in this, but it would be nice to talk about this topic again after a couple of years. Okay? So, I think everybody knows this because you saw this for at least 2 years. This is a protein. This is the spike protein that goes in the COVID virus in the cells. And most of the mRNA vaccines leverage the existence of this protein. So proteomics was the main motivation for the research on distance geometry in the beginning. Okay, so that's why I'm starting with this to motivate. So most of the biochemistry or biophysics guys, they perform some experiments on proteins to try to extract the most data they can. And most of the things that we've been working with are with kind of crystallography data and nuclear magnetic resonance data to extract distances, and these you can see it kind of a matrix, and you can estimate distances between hydrogens here, and we use some Ramachandran knowledge on the peptide plane to estimate more distances. And then what we want is, we know distances, or we estimate distances between pairs of atoms, okay? And then we want to try to configure this protein or the molecule. We want to have the shape to calculate the Cartesian coordinates for the atoms based only on distances. So this wedding started when this guy that I had the pleasure to meet in the Amazon forest in 2013, in the middle of the forest. We went like in a boat for 40 minutes until a resort with onças and lots of beautiful and savage animals. And I met this savage animal from biochemistry and math, Professor Gordon Crippen, who was the first guy in 1977 when he said, okay, I think we can apply distance geometry to configure a protein, why not? So this was a novel approach to calculation of a conformation of a protein using this tool. And he based his knowledge on this very old book from Leonard Mascott Blumenthal, Theory and Applications of Distance Geometry. It is not a common geometry book. This is a very, very hard book to read. You know those books that you open the first page and say, okay, your notation is not my cup of tea. Like, we are not talking the same language. The notation is very bad. But what he does is to analyze semi-metric structures, okay? So you have a metric space, you relax a little bit, you have a semi-metric space, and then he studies the behavior of such semi-metric spaces, and he goes talking about Euclidean semi-metric spaces, projective semi-metric spaces, non-Euclidean semi-metric spaces, thinking on addressing to Euclidean geometry and non-Euclidean geometry as well. Sorry. Okay. So, he together with Tim Havel, they defined in 1988 the fundamental problem of distance geometry. So, given the distance and chirality constraints, chirality is like when you look to your hands and when you have a mirror, okay, and the image in the mirror is kind of symmetric in the reflection, we say this is chiral. Okay, so the hands are chiral. So you have chirality about this. When it's chiral when the object is not equal in the image. If it would be like this, so it's achiral. So the constraints were distances and the chirality of the molecules. And he wanted to find one or more conformations which satisfied those constraints, or to prove that no such conformations exist. Okay? So look, it's kind of a little bit fuzzy here to say that, what is this problem? Is it a search problem or is it a decision problem? So this problem evolved. In 1978, Yemeni was researching on sensor networks, and he talked about a problem close to this, which he called the positioning problem. So he said that the positioning problem arises when it's necessary to locate a set of geographically distributed objects using measurements of the distances between some object pairs. Okay, so this is well written for me to understand the aim, what he wants to do. In 1975, again working on sensor networks, John Sachs defined the problem as K-embeddability problem. Because now Sachs said, okay, but this isn't an embeddability problem because we want to embed the graph, the structure, in a space, and the dimension of the space can vary. Why not? So the dimension of the space is this K. So the graph is said to be K-embeddable if there exists an embedding of G in the K space. Okay? It seems to be the same thing, but for me this is well defined in starting to to get things a little bit more more general. Okay. Okay. But remember that I started this talk talking about molecules, about proteins. And then suddenly I went from proteins to graphs and to sensor networks and so on. But I will come back to molecules now because all this, both discussions went in parallel. One discussion is on the applications of distance geometry. And the other discussion is the application strictly to molecules, to proteins. Okay? So the word graph started, I don't know if you know that, but the word graph came from a molecule study. They've been studying molecules, and they had only the chemical molecule that we know, H2O, CO2, those things that we talk every day, like beware on CO. No, not department CO. Beware on the monoxide, carbon monoxide. Beware of this, not department. Department is CNO, not CO. Please, David. Sorry. And they said, okay, but beyond, more, instead of talking only on the chemical compounds, we can try to analyze the links, how they are linked. And then we studied in school those links, like, carbon, and we have a joke, like, carbon goes to jail and have 4 calls, you know that, okay? But it was the Sylvester that I guess you know Sylvester well, from the law of inertia. And Sylvester, he published a note in the so prestigious Nature about, in 1878, about a relationship between chemistry and algebra. And he said, okay, there's a graphic formula. Okay, and this graphic formula was reduced to graph. And they started to look to these things that we know very well as graph, a chemical graph. And so on, Arthur Cayley and the other guys that worked with graph theory, they started to use graph, started using graphs. They said, oh, now we have a theory, and graph theory came out, okay? Remember when I talked about Crippen and Havel problem, the fundamental problem of distance geometry? It was kind of a decision or a search problem. So then we can, I'm telling you guys that we can formulate the problem as both. We can formulate the problem, the distance geometry problem, DGP, as a decision problem. So we want to determine if there exists an embedding, and this embedding people call realization, Henry Volkovich calls configuration, some guys call confirmation, so all of them are synonyms for me. Okay, I'm very interested in say that if there is or there's not an embedding of this weighted graph, I have a weighted graph, okay, simple and undirected graph. So it has no cycles, it has no singularities, and the edges are all weighted, okay? Non-negatively weighted. So that this embedding is isometric in the sense that all the weights coincide with the distances of the points related in the embedding, okay? Okay, so you can decide if there is or there's not an embedding, or you can look to find embedding, to determine, to say, here, I have an embedding, okay? And this is the problem, particularly, I am interested. I'm not interested in the decision problem, I'm interested in the search problem. So I have to look to the search space. So we have to define which is the search space that I have to look. If you want a good survey on this theme, you can look to this paper at SIAM Review from 2014 of Leo Liberti, Carlisle Laver, that was my supervisor in PhD in Brazil, the Professor Nelson Maculam, and Antonio Mucurino. Carlisle and Nelson from Brazil, Liberti from Paris, and Mucurino from Rennes, both in France. The three of them, Liberti, Lavore, and Mucurino, have been my co-authors in the paper that I'm going to talk at the end of this talk. Okay, so we are not interested in designing molecules in R10. Okay, to say to my computer, okay, draw for me a molecule in R10. He's going to say, okay, there's a molecule, but I cannot show you yet this molecule. So when we want to work with molecules, we have to go to R3. So we have to fix the K. And this is another thing, that K is free. You can ask, is there an embedding in K equals 1? Or for the very same problem, is there an embedding for K equals 10? Or is there a threshold for K for my instance? There are lots of problems that we can figure out. Lots of them. And Crippen and Havel, they worked with this embed algorithm. Working with this is, we want to minimize something. We want to find a confirmation because the search space is continuous. You have to look, like you have a fixed distance that you have to fix in a continuous space, okay? So they said, okay, we have to look for this, but we're supposed to have a reference. What do we want? Okay, we want to minimize something. What? We want to minimize energy. Okay. And they got this embed algorithm, and you have lots of papers here about this. But some guys have been working with other things in optimization, and they said, oh, nice. I read your paper in the newspaper about molecules. I think we can talk more about optimization on this. Okay, so Jan Dillot published a paper on multidimensional scaling when he had, look, a matrix of dissimilarities, distances, weights, a configuration matrix, a distance matrix and associated with the configuration, and a weight matrix. This weight is like if I want to erase any data, or if I want to, as we penalize things, like I want to not give so importance to this distance, but I want to give more importance to that distance. So you can scale this with a weight matrix. And he came out with this function. He said this is a stress function. And we are calculating the stress on the configuration X and on the matrix of the similarities delta, like this, okay? Look, sometimes you don't see this half. What is not good because there is a square here that when you want to get the derivatives, The 2 will come here, and then you have to work with this 2. So most of the guys don't work with this. And what guy said is that, okay, this is, this is a good function to apply, but I think we have to smooth this function a little bit. So they came out with this new function, which is the smooth stress function. And now, remember that our problem is to solve a nonlinear system. We have a nonlinear system, and this nonlinear system is overdetermined. Okay? So we have to solve this. And to solve this, the solution of this is the solution of this optimization problem. You have lots of work here, Havel, Glunt, and Hayden, and Radin, and Hendrickson working on this. What's the problem? The problem is that you have many local, non-global minima. Lots of. So the algorithm gets crazy and very slow. So the problem is very hard. The John Saxe said in 79, this problem is NP hard. So until now, we are trying to solve this. Like, we are trying to figure out new algorithms who does this more quick and more accurate. For example, I'm working a paper now that we are trying to put some, trying to use some structures from the protein data bank to try to teach this to a neural network. Like, can you learn with this data and tell us if we are going well or not in our search? Okay, and we are getting good results. But it's not submitted yet, so I will not talk about this yet. Then, after the optimizers, not the pessimizers, the optimizers, they came and said, okay, we can collaborate, we can go on, we can work on this. The guys from combinatorics said, oh, we can work well as well. Why not? The graphs are here underlying. So let's work on this. And you have here lots of work on Jorge More, so prestigious Jorge More, Kefen Dong, and Zijung Wu, and Di Wu, and a good bunch of guys have been working on this. Like, okay, let us put some assumptions on the vertices. If we have 4 positions, we know 4 vertices. We know the positions of them. And it's very easy. You put the first one in the origin of the system, the second one in the x-axis, the third one in the xy plane, and the fourth one you get. Like, it's very, very simple to calculate. So it's very simple to find 4, to position those 4 vertices. It's very simple. The problem is that you have 5,000 vertices to position. And you have the distances, they are not like, they don't have a pattern. You have to try to figure out how to have anchors and try to anchorize your search. Like, I will put an anchor there, an anchor there, an anchor there, and then try to position this vertex, and so on. And they said, okay, after that, what's going on here? For each vertex I want to position, I'm supposed to have at least 4 neighbors, 4 anchors. So that with those anchors, I can solve this linear system. Okay, 2 problems here. First one, there are lots of molecules that you can't configure it, the whole molecule. Because the amount of distances you have allow you to configure only a partial part. Okay, so you have a partial part. The second problem is this linear system is very small, but very, very sensitive. He cries a lot. It's a problem of emotions. He has a problem on his emotions. Okay, the condition number is very bad, very, very bad. Okay, what you can do is, and they did, let's try to change the anchors. Okay, we get 4 anchors. Calculate the system. Look to the matrix. Oh, it's not a good condition number. Okay, let's try to find other 4 anchors. Okay, I found it. Let's look to the condition number. It's bad? It's worse or better? Okay, it's better. Okay, but better, but not so good that I wanted. Let's look for more. You know, look, it's crazy. I have to go looking for 4 and 4 for sets of 4 neighbors. Okay. What I tried to do was an overview, and so far, so that you can understand a timeline on the happenings to get until this problem. What is this problem? Those guys from these guys, they said, okay, we want to try to look for a better search space for us. And so that we want to look for some additional assumptions. So I have a graph, a weighted graph, simple. And this graph is undirected and simple. But now I put a total order relation on the vertices. Look, when you see a molecule, look for a molecule, okay? H2O. You have 2 H's and 1 O. Who is the first atom? Who is atom 1? Who is atom 2? You can fix. I fix 1, I fix 2. Doesn't matter. Okay? Now it matters. Now we want to say that atom 1 is 1 because of this. 2 is 2 because of this. 3 is 3 because of this. And this total order relation is that we have the discretization assumption, which says that each 4 atoms in the order, subsequent atoms, vertices, not atoms. Sometimes I will say atoms, but when I say atom, you read vertex, okay? Each 4 vertices in a row, they have to form a clique. They have to form a complete subgraph, okay? And the distances or the weights, they have to obey the strict triangular inequality. We don't want to have at each 3 in a row, we don't want them to be like to have the equality here. We don't want. Because this equality would put those 3 vertices in a line, and we don't want that. Okay, we don't. That's why it's a non-collinearity. So here we have an example. What time I have? 20 minutes? Okay. So look, imagine that we have now 7 vertices, okay? And this is my instance. Lots of edges, okay? I have a click here, a 4 click. Now another 4 click for the 1, 2, 3, 4, and now 2, 3, 4, 5. It's not a Lou Bega song. And now 3, 4, 5, 6, and then 4, 5, 6, 7. So the first assumption is obeyed in this graph. Okay, when you look to this, you can say that, but you have to look like this, look this way. What is the question here? When I have a 4 click here, what I know is that I can make 3 spheres and look. I want to know the position for the 7th vertex. And I know the position of the 4th, 5th, and 6th. And what I know is that this guy lies in the intersection of the spheres with this radius in this center, this radius in this center, this radius in this center. This radius in this center. Okay? So we can look to a sphere intersection. Now it's good because look, if I have those assumptions, at each step, I'm in something like this. What is good? Because in R3, I have at most 2 possible positions. In RK, I have at most k minus 1 possible positions instead of a continuous search space. It's impossible to have this kind of thing. Some guys proved this once. I will not talk about this because it goes to algebraic geometry, and I don't want to talk about this now. And what is the question? The question is that the probability of having only one is 0. You can measure that. The only possibility is that either you have 0 or you have 2 possibilities. In this intersection, okay? So we consider the partition of the set of edges into two kind of edges, the discretization edges and the pruning edges. The discretization edges are these ones. If you look to a matrix, the distance of a guy for itself is 0, okay? And all those 3 distances you have, all those 3 you have, all those 3 you have, okay? And that's why we can look to this kind of landscape, 2 solutions with probability 1. When we say with probability 1, we say that it happens almost all the time. It doesn't happen always. It happens almost all the time, but there is a countable set. There is a set with measure 0 in that it can happen. So that's why it happens always. When I say something here, you have to have this in mind. It's happening with probability 1. Okay? We can, why not, have other kind of distances that are not given by the assumptions. Those distances, we call them pruning edges, okay? Because they are extra. They may exist, but they may not exist, okay? The discretization edges, they are always here. The pruning edges, we don't know. It varies. So this is the matrix of my example. The black ones are the discretization, and the red ones are the pruning edges. Okay, I know 1 hour talk, sometimes we get a little bit tired. Okay, let's go on. So in this paper, those guys, the same guys from the paper I showed before, they designed a recursive algorithm based on the branch and bound. They looked at the branch and bound and they said, okay, we can have a branch and prune strategy because our assumptions now allow us to have a search space like this. Our search space now can be designed as a binary decision tree. The first 3 vertices in R3 are fixed. They can be fixed. If we are in R k, here we have k vertices, okay, the first k. For the fourth one, or the k plus 1, the k plus 1 on, you have 2 possibilities, okay? And they decided to explore this search space in a depth first search, okay? So what is a solution for me? A solution is when I have a structure from the root until get one leaf. Okay, so this black structure is a solution. This black is another one. This black solution, this black one, another one, and so on. Okay? What about the red branches? They've been pruned away because they're infeasible. And how can I say, how can I talk about feasibility? I only can talk about feasibility because of the red extra pruning data. If we don't have pruning data, all the tree is feasible. Not only possible, but feasible. Okay? And so this kind of distance, those red values, they will guide us from the root to the leaf. They will give us an orientation in our exhaustive search. It continues to be an exhaustive search. So I have to look for all the possibilities. But it's not so exhaustive because I have some hints from the oracle. And the oracle says something for us. When I get, for example, when I get to the 5th atom, 5th vertex that I calculated, I have this distance. And I have the position of 1 and the position of 5. Okay? I calculate the distance. I look to the value I have. If it's infeasible, I throw it away. And you can throw away because you have another opportunity to test. Because there are 2 possible positions. Okay? Good. Okay. Okay, so this is the tree. And look. Look, this is solution 1, solution 2, solution 3, and solution 4. Okay? Solution 1 and solution 4. Does it seem to be looking in the mirror? 1 and 4. Solution 1 looks in the mirror and sees solution 4. Oh, how I'm good. My image is still a solution. Solution 2 looks to the same mirror. The mirror is given by these guys. They set a plane, and this plane is a mirror. Okay? This guy looked to the mirror and see as solution 3. Said, oh, I fit well in my outfit. But these guys, they look and say, oh, I see nothing because I was pruned away from the light. And they could use group theory, permutations, symmetries, those things that we learn in group theory, to prove that there is a group acting in the solution set. You can put a group acting in the solution set And those symmetries are real, okay? So what is a symmetry vertex? A symmetry vertex is a vertex like this, the blue one. I don't know anything here for the past. And I don't know anything here either. If I have a block here, if it gives a block matrix with no information, this guy is a symmetry vertex. This is the paper that they proved the symmetry. Horrible. It's very difficult to read, but it's everything there. Now, you know that with probability 1, the number of the solutions is a power of 2. Okay, so when you start your algorithm, you know at most the number of solutions you can get. Okay? You can precondition your structure to know that in advance. For example, this matrix is about the example I'm giving in the all lecture. Here we have 2 symmetry vertices. The 4th vertex is always a symmetry vertex, the 4th, okay? And we have the 6th vertex as a symmetry vertex as well, okay? So we have 2 symmetry vertices. And if we have 2 symmetry vertices with probability 1, I have 4 valid realizations. And that's what I see in the tree, 4 valid realizations. Here, I have a symmetry according to this plane. And here, I have other symmetry according to the plane made by the 3 positions here, and another symmetry by the plane made by these 3 positions here. Okay? So if this guy is a symmetry vertex, the k vertices before him in the order, their positions define an hyperplane. Okay? And this hyperplane is a symmetry hyperplane with probability 1, okay, always. So they said, okay, instead of looking for all the solutions, my algorithm can look just for one solution. If I find one, I can go using partial torsions, okay, partial torsions to find all the other solutions. So it's amazing. Remember, in the beginning, I was in a dark space, looking for solutions. Then, I put some assumptions and said, okay, now it's a little bit more tractable. I can look for solutions in a binary tree. Now you were supposed to explore just a part of the tree. It's not necessary to explore exhaustively all the tree anymore. Okay? With probability 1. And the algorithm now is called branch and prune 1. Okay? When I say branch and prune, it's the algorithm that finds all the solutions, the valid solutions. Explore all the tree. Okay? The whole tree. Branch and prune 1 is the algorithm that finds the first solution. I got to a solution, it stops. Okay? It halts, and then I use the symmetry data to find the other ones. Okay? Okay, now this is my gang for this paper. Douglas Gonçalves, that had worked with Leo and Henry, and Carlile Lavore, my supervisor in the PhD, Leo Liberti and Antonio Muccherino. This paper came from my PhD thesis, and I said, okay, is there a way to cut the instance into small pieces, realize the small pieces independently? I was with parallel computing in my mind, okay? We realize those pieces independently, and then we merge the pieces, the solutions, so that I have the less effort possible after merging. I don't want to look for validation of the structure. The less pruning data I have to use after the mergings, okay? So, my question was, what's the number of subproblems I have to solve? What's the size of each subproblem? Does it matter how to figure it out? The answer came from the symmetry vertices. Okay? So look. Here I have the fourth vertex, which is always a symmetry vertex. I have here another, the 11th vertex is a symmetry one because I put zeros, but it's not zero, okay? I just put zero when it was, because it's more beautiful than a question mark. But it should be lots of question marks here. If I have lots of question marks here in this block, this guy is a symmetry vertex. So I have three symmetry vertices here. The fourth one, which is always the 11th and the 16th. Okay, in the order. So in this case, I can cut my instance into three subproblems. So I have the first subproblem. I solve this subproblem. And this subproblem will give me two solutions with branch and prune, and one solution with branch and prune 1. This subproblem will give me two solutions with branch and prune, and one solution with branch and prune 1. And the same for the third piece. When I merge a partial solution here with another partial solution here, look, there is no data so that I have to test. They are feasible. Inherently feasible. The distances told us how to cut the instance. Okay? And the same here. When I take the part, the piece, and I want to attach this sub-solution, I have nothing to test. So at the end of the mergings, all the merged structures are feasible, and they are all solutions for the algorithm, for the problem. We did this. I don't have time, but you can look. You can ask me for this talk slides, or for the paper. I made a covering. Okay, I started working with coverings and the graph covering of the graph. So each covering induces a subgraph, and I looked to the union of those induced subgraphs. I said that what is locally feasible for me, so this guy, a solution for this piece is locally feasible. Okay? If it's a solution here, but it's not a solution for the rest, this thing is locally feasible for me because it's feasible just one part. Okay? But I'm looking for globally feasible structures. And that's what I did here in the results. This very different guy is how we can generate. That's why I call Genesis. I didn't have a better name. But it's a Genesis set. It's a generator. Okay? I didn't use generator because we had generators for other things. Okay, so this is a problem when we give birth and want to give the name, as I did with my son. Okay, I gave birth, beautiful, looks to my wife. What the name? I don't know. Junior, nah, so selfish. Okay, and this is how to generate our set. This set is the smallest set that contains all the symmetry vertices that we need, okay? They are here. So you start with it's an algorithm, build-up algorithm, like you start with, you pre-process the graph, like lots of vertices, and you are cutting until you get only the vertices you need, okay? In fact, it's not vertices. There are intervals. I need intervals. And the intervals are overlapping. Look, here, I forgot to say that. They are overlapping. They always have these overlaps, always. Okay? So we have here an interval from 1 to 10, and the other one from 7 to 15, and the other one from 13 until 20. Okay? And the overlap is always size K. It's size 3 because I am in R3 in my example. But if you are in RK, the size is K. I saw something like this, Leo, in your talk. It's like this. I don't know if it matters or if we can like talk the same language. I made some computational experiments with artificial structures. I didn't make experiments with proteins, real proteins, because these results are from 2018, okay? And we didn't went further yet. If you want to go further with me to talk about it, I'm here, okay? That's it. Thank you very much. Happy New Year for everybody. It's an honor to talk in Professor William Toots colloquium. Thank you, Sam, for the invitation. Thank you, everybody.
Yeah, thank you for the talk. If anyone has questions, please wait, and I'll pass the microphone to you.
Thank you very much for the talk. You have this sequence on the vertices, right? That is really helpful. You just need to look at like the ones that came before to decide the next position. That's where like that's how you imposed some finite structure for you to look at. Is the motivation the algorithm that you came up with, or like from the protein context or some other context, like you can see where, you know, like the data arises naturally, where that came from?
Excellent question. Thank you. They started with the order, and then they made it's a virtual order in a real protein because you have to repeat some vertices. You have to repeat some atoms. When you walk, you pass through an atom, and then you go further, and then you come back, pass through that atom again, and that atom is counted twice, okay? That's why we treat proteins. When they designed the algorithm, they thought it was like the protein, but it was not. Because proteins, it's a chain of amino acids, and the residuals can be very difficult to manage. Proteins with proline are the worst ones.
Thank you.
You're welcome.
So do you have a proof that this special case is still hard?
What?
Do you have a proof that the special case is still NP hard?
The proof is in, I don't have a proof. This cut?
So you're solving a special case of the problem that Sachs proved is NP
Okay,
hard.
yeah, it's an
Is the special case, is there a proof that the special case is still NP hard?
No, there's not a proof. They just assume that it's NP hard because it's a subcase. It's a subset. So all the examples of the general problem, and we are working with a subset of examples. So it's still NP hard.
It goes that way.
What?
I don't think it goes that way. You're dealing with a subset of the examples.
Yeah.
Why aren't those?
Yeah, because I'm imposing more assumptions and going like strictly to subclasses of, to a subclass of. But I didn't see a proof that it's still NP hard. I didn't see if there is.
Okay.
So, now I think I got the question now. I'll take a look. I think there now. I said that there is not, but I think there is now. I remember now that they dealt with the subset problem. Subset problem. I guess it's something like this. I'll take a look and then I can show you. I'll take a look. Okay. I'm not sure. Good question.
If there's no other questions, let's thank Felipe again.
Thank you very much.